We're group 24 and we're solving problem 1118 from the textbook. It's a frame problem with a distributed load and needs to be solved by the slip deflection method by matrices. First, we're starting off looking at the problem, which is, as I said, a frame with fixed ends and fixed joints and a distributed load. Since members A, B, and CD have fixed ends, theta A and theta D are equal to 0. And since we have both fixed ends and fixed joints, there is no deflection. It is also given that EI is a constant, so we can move on to look at the matrix we'll be using to solve this problem. We wrote our matrices equal to the shear and moments of each member to this constant matrix that will give us the moment and shear equations for each value needed. Next, we'll look at the breakdown of the moments on each member. We'll break up each member into their own moments, and we'll start by using the sign convention that moments upwards are positive. So we'll start all moments are positive on MB, AB, BC, and CD, and we'll look at specifically at the moment acting on joints B and joint C, which will be equal and opposite, so we'll know how to find our equilibrium for those points.
The resulting moment equations are from the matrix explained in the part before. We have no deflection in this problem because the entire frame is fixed. Looking at moment equation for AB, we have no theta A because A is at a fixed end. This leaves us with negative 2 EI over L theta B because there is a distributed load on member BC which causes a rotation at theta B. Looking at the moment equation for BA, again theta A is gone because it is at a fixed end, which again leaves us with 4 EI over L theta B. Looking at moment equation BC, we're going to keep both theta B and theta C because there's a distributed load across the entire member of BC. We also have a fixed end moment because of the distributed load. This fixed end moment, which can be found in the back of the book, is negative WL squared over 12, which is also 14.4 kips per foot. Looking at moment CB, we again are going to keep theta B and theta C because of the distributed load across member BC. The book says we're going to have a positive fixed end moment, WL squared over 12, which again is 14.4. Looking at the moment equation for CD, we're going to keep theta C and we're going to take out theta D because theta D is at a fixed end, which leaves us with negative 4 EI over L theta C. The final equation, moment equation DC, we're going to keep theta C again, and we're going to take out theta D because of the fixed end. This leaves us with our moment equations.
From our moment diagram, we could see that at equilibrium, MBA equals MBC. Rearranging that equation, we get MBA minus MBC equals 0. Plugging in the equations for the moments we found previously, we have MBA in red parentheses and minus MBC in green parentheses. Solving this equation, we get equation number 1 in blue. Also from the moment diagram, we see that MCB equals MCD at equilibrium. Rearranging this equation, we get MCB minus MCD equals 0. Plugging in our moment equations we found previously, we have MCB in red and MCD in green. Since we have two unknowns, theta B and theta C, solving this second system of equations will give us our another equation, which is listed in blue. Now we can plug equation 1 into equation 2 and solve for both theta B and theta C. Theta B will equal 39.293 over EI, and theta C will be equal to negative 39.283 over EI. Then we take those values of theta B and theta C and plug them into the original moment equations where necessary. We will get MAB equal to negative 3.93 kip feet. MBA will equal to 7.86 kip feet. MBC will come out to be 7.85 kip feet. MCB will be 7.86 kip feet. MCD will come out to be 7.86 kip feet. And MDC will come out to be negative 3.93 kip feet.